Hey there, and welcome to This Explainer. Today, we're taking a seriously unexpected journey connecting two seemingly disconnected worlds, abstract algebra and classic geometry. We all know right triangles from our earliest days in math class, maybe with a little bit of dread, but today we're going to look under the hood and explore the hidden engine that actually builds them.
Here's our roadmap for today. First, the hidden algebraic engine. Second, generating Pythagorean triples. Third, the three behaviors of primes. Fourth, splitting primes. And finally, the hypotenuse rule. Let's dive right in. So, part 1, the hidden algebraic engine. Let me ask you something. Where do right triangles actually come from? When you were back in school memorizing a squared plus b squared equals c squared, you probably just thought of them as, basic static shapes. But there is actually a much deeper hidden algebraic source code that's actively generating them behind the scenes. To read that source code, we need to get our vocabulary straight. A Gaussian integer is really just a complex number. We write it as z equals a plus bi, where a and b are just your standard everyday integers, numbers like 2, 3, or -5. By stepping into this complex plane, we're about to unlock some absolutely incredible geometric secrets. All right, moving right along to part 2, generating Pythagorean triples. This is where the mathematical magic trick happens. If you take a Gaussian integer, let's just call it m plus ni, and you simply square it, something wild happens. Expanding that complex square instantly spits out the exact pieces of the classic Pythagorean formula. It's literally like pulling a perfectly formed triangle right out of an algebraic hat. Notice how these totally abstract complex numbers perfectly map to physical triangles you'd actually recognize. Like if you plug in 2 plus I, boom, out pops the famous 3, 4, 5 right triangle. Plug in 3 plus 2i, and you get the 5, 12, 13 triangle. The arithmetic of complex multiplication is directly generating the geometry of right triangles. How cool is that? Now, just a quick clarification here. If we want what's called a primitive triple, meaning the sides don't share any common divisors other than 1, like that 3, 4, 5 triangle, our starting numbers m and n need to be coprime and have opposite parity. So basically, one has to be odd and the other has to be even. Which brings us to part 3, the three behaviors of primes. To understand the limits of what triangles we can actually make, we have to look at the fuel for this whole engine, prime numbers. When we look at ordinary prime numbers inside this realm of Gaussian integers, they definitely don't all act the same. Every ordinary prime falls into exactly one of 3 distinct behaviors. First, the prime 2 ramifies, which essentially means it becomes the square of a Gaussian prime. Second, primes that are 1 modulo 4 actually split into 2 conjugate Gaussian primes. And third, primes that are 3 modulo 4 remain inert, meaning they stubbornly stay prime and just refuse to break down any further. Let's zoom in on why that difference exists. Modulo 4 just means we're looking at the remainder when we divide a number by 4. If a prime is 3 modulo 4, it is mathematically impossible to factor it into a sum of 2 squares. Why? Well, because perfect squares modulo 4 can only ever be 0 or 1. You can add 0 plus 0, 1 plus 0, or 1 plus 1. But there's no way those sums are ever going to equal 3. It's a fundamental mathematical roadblock. Okay, moving to part 4, the deep direction, splitting primes. We're going to take a deep dive into this fascinating modulo 4 rule and figure out why those specific primes, the ones that are 1 modulo 4, actually do split. It all comes down to an incredibly elegant 3-step proof. Step 1, we use a concept called Wilson's theorem to produce a square root of -1 modulo p. Step 2, that mathematical consequence creates a situation where our original prime, p, can no longer be a Gaussian prime. And step 3, since it's no longer a Gaussian prime, it must factor non-trivially, neatly giving us a sum of 2 squares. For those of you who really appreciate the rigorous mechanics, Wilson's theorem sets up this beautiful pairing. And that pairing ultimately proves that a prime equivalent to 1 modulo 4 perfectly divides into a complex product. That little consequence right there immediately shatters the prime status as a fundamental building block in the Gaussian integer world. And here is the final piece of the puzzle. Because p is no longer a Gaussian prime, it has a non-trivial factor. By taking the norm of this factor, we see it absolutely demands that a squared plus b squared equals p. This definitively proves why a prime that is 1 modulo 4 always splits into the sum of 2 squares. And there you go, we've officially survived the quantum depths of the primes. Now for our final section, Part 5, the hypotenuse rule. It's time to zoom back out. Let's connect this microscopic prime behavior directly to the actual physical triangles we draw on paper. The core concept tying this entire explainer together is perfectly summed up by this quote from our source material. This multiplicativity is the algebraic engine behind the entire construction. The norm map we've been using is multiplicative, and that mathematical property, that's the true hidden force generating these geometric shapes.
So here is the absolute crucial point. It's a hard, fast rule. Only split primes can be hypotenuses. Because of everything we just learned about inert primes, a prime like 3 or 7 or 11, anything that's 3 modulo 4 can never ever form the long side of a primitive right triangle. It never factors in the Gaussian realm, so it literally can never appear as a hypotenuse. The geometry you see is strictly governed by the arithmetic you don't.
Which brings us to a really fascinating final thought. Every right triangle you've ever interacted with ultimately traces back to unique factorization in the Gaussian integers. So if the arithmetic of right triangles is really just the arithmetic of complex multiplication, well, what else is hidden in the primes? What other geometric shapes are just waiting to be uncovered down in the deep quantum level of numbers? I hope this explainer sparked your curiosity to look at the basic math around you just a little bit differently.